In the next subsection, we'll look at the first example of a more interesting code, and that's Huffman codes. I think many of you will have seen some of these, but I want to give everyone a chance to follow on. It's a very useful technique that has found its way as a one building block into many practical compressed formats, and is also a beautiful algorithm. So where do we come from? This is still the part about character frequencies. So the redundancy we'll exploit is that some letters are much more frequent than others. Here's some graphic way of representing that for English text. And we'll always encode to binary here. Most can be generalized to our larger coded alphabets, but it's hardly ever used or hardly ever interesting. If we fix the coded alphabet to just binary 0, 1, we can use just sigma for the source alphabet, because the source alphabet will appear many, many times on the slides, so having a shorthand for that is useful. The intuition should be clear. Huffman is a variable length code. It gives one code word for each of these letters, say if that's your alphabet. And of course, we kind of want the frequent characters to have a short code word, and because we can't have everything short, you have to assign longer code words to some of the less frequent characters, longer than in an ASCII code. But how to exactly do that? To formalize the problem, this is what our input will look like, and it's pretty much this table in a general sense. We're given an alphabet, so what are all the symbols that can occur in the text, and weights for these symbols that just represent which ones are more important or which ones occur more often. Will be generic, so these are just some numbers assigned to the letters, but you can think of them as probabilities in a text or relative frequencies in a text. And the goal is to find a prefix-free code that assigns to each of the characters in the alphabet one code word. And it should be a prefix-free code so that we can represent it as a trie as before. And the goal is to minimize this sum, which is summing over all the characters in the alphabet. That's the length of the code word, times the weight that we assign to that character. And so if you, the special case, I don't know, did I put this on the slide? Yeah. The special case when the weight is the number of occurrences of a character in some source text, then this sum is exactly the total size of the coded text. Right? Each character W, each character C occurs W of C times in the source text. So you will have to write down its code word W of C times, and it needs length of E of C bits. So we're really asking for the best possible character encoding of a given text, which is, I mean, if you think about it, it's quite ambitious. Remember all these hard impossibility results about Kolmogorov complexity and these things. It looked like not much is possible in the general compression sense. And now we're asking for the completely optimal character code. But it turns out in this case, it is possible. And the key is that we're restricting ourselves to individual symbols. We encode one symbol at a time. And that is a much more restricted scenario. It's even better than that. It's not just possible, it's also a very simple or simple-minded algorithm. In a way, it's called a greedy algorithm, where greedy has really a technical meaning in that sense. It says the myopic approach to take what currently looks best is actually giving you the globally best solution. It's hardly ever true in life, and it's also not often true in algorithms, but sometimes it is. And finding Huffman codes is one of these, or finding the optimal length character codes, prefix-free codes, is one of these examples. And so Huffman's algorithm works as follows. You have all your characters with their weights. Now you find two characters with the lowest weight. Intuitively, again, these are the least important ones, so we can assign a longer code word to those two. And what we do is we take those two and say, okay, we don't know what they will at the end be encoded to. They will be encoded to some string u, and then I'll use one more bit to distinguish between A and B. So I'll decide for now the code word for A will be some string u and then followed by 0, and for B it's some string u followed by 1, so I can distinguish the two. But I don't know what u is yet. Okay, but I know that the 2 can now be treated as 1. So I create from the two single characters, from A and B, I create this boxed character. I've used the same notation before, right, in when we talked about suffix arrays. So just imagine this as a new symbol that consists of those two together. It's just an imaginary thing if you want. And we'll set the weight of this new symbol as the sum of the weights of the original one. The whole idea is just we need a way to get to this u. And the way we'll get there is to say, oh, these two characters share their code word up to this point, and we already decided what happens after it. So we combine them into one character and recurse. So we call the same algorithm on the remaining characters, but we have made the problem one smaller, right? We took two characters out and one u in, that's still a -1 in total. So if we keep doing this, we will eventually end up with a single character, and then we can stop. Let's talk about how to implement that after the example. So here's an example, and I'll do it like we will essentially always do it in this module. We'll use as weights the frequencies in a text. So we start with the source text, lossless. It has just these 4 characters, so I'll assume we just need those 4. And I did the counting for you. So this is the starting point. And now remember what Huffman's algorithm did. It said, try to find 2 characters that have minimal frequency. So in this case, that should be these 2. They're both of minimal frequency, 1 in this case. And then I lump them together. Now graphically, you can nicely represent this as a little code trie. And the other ones can also be seen as simple code tries. They're just single leaves, so there's not much to them. But once we combine those two, these are the ones with the minimal leaves, then we decide one is the 0 child, one is the 1 child. And we create some internal node. We don't know the path to the root from this yet, but we'll get there recursively. And we assign this one as weight, the sum of the weights of the children. Okay? And now we keep doing the same thing. So the next step is, again, find the ones with minimal weights. Well, it's these 2. And so again, we combine those. So we create a tree that has, as children, the 2 nodes from before, or the 2 subtrees from before. In the general case, what we get is an entire tree here. And so here we combine those in the same way. One gets the 0 child, one becomes the 1 child. And we create a new internal node with, again, some unknown path to that. But we'll just leave it as that for now. OK, one final step. There's only these 2 left, so not much choice. So we combine those. So again, you see this was the subtree from before. This was the other subtree. And we just combined them like that. And that's the Huffman code. Now, one thing I skipped was about the implementation. How would you implement this code using data structures you've already seen so that it runs fast? The potentially expensive part is this, where you have to find these 2 characters of minimal weight. But we've seen exactly the right data structure for that, namely a priority queue. If you keep all the characters in a priority queue, you can do extract min twice. That gives you the 2 characters with currently minimal frequency. And then you create this new boxed character and put it back in the priority queue with the sum of the weight as its priority. And that way, you can do this step in log sigma time. Sigma is the size of the alphabet. It actually gets faster over time, but the first time it takes log sigma. And similar, so the insert here also takes log sigma time in our priority queues. And so the recursion itself, you can unroll that into a loop if you want. I think the example showed that quite clearly. So you're doing this overall sigma times until you end up with just a single tree. So the total time will be something like sigma log sigma. We also call this final result the Huffman tree for, I guess, obvious reasons. It's just the code trie for the Huffman code that the algorithm generates anyways. And that contains pretty much all we needed. We can then use this to compress our source text. So if we do this, well, I didn't put the table here, but you can find this. The code word for L is 0, 1. The code word for O is 0, 0, 1. And then S gets the shortest. It's just a 1. And so on. So you get this coded text from our text lossless. And then you can compute the compression ratio as we defined it last time. So it's 8 characters in the source text. And we have 4 characters in the source alphabet. So that gives you this 8 times log 4 for the size of the source text. And if you do the counting here, it's 14 bits in the coded text. And so you get a slight reduction in space. It's not super impressive because the string is so short. But at least it's shorter than the trivial way to represent it. Okay, a very important slide for all the application problems on exams and class tests and so on. I have to see if I can put maybe a... Okay, I'll check this offline. The procedure from above is ambiguous in various ways. If we have if we have ties for what is the lowest weight, it's not clear which two we should use. And when we combine things, there's a symmetry in which one is the left and which one's the right subtree. It all doesn't really matter that much. The code will have the same length, but it's a different code because if you swap some things in the tree around, you swap a 0 and a 1. If you combine things in a different order, you get slightly different code words. So do me the favor and memorize, or well, I always... If there's a problem like this on the exam, I will always reproduce this box. But train yourself to obey these rules so that you always get a unique result. That makes checking those much, much easier. And so I'll require you to use that rule. When we select 2 characters for the minimum, then if there's ties, we'll always break the ties by the alphabetic order. So if there's A, B, C, and they all have weight 1, and that's the minimum weight, you don't take C and B, you take A and B, because they're smaller in the alphabet. That's the first one. Now, if you have a whole tree, you take the smallest alphabet anywhere in the tree, the smallest symbol anywhere in the tree. Because if you have 2 trees, they might be incomparable otherwise. But you can always find the one that's earliest in the alphabet. Second rule is when you combine 2 trees, and there is one that has a smaller weight than the other, you could put the one with a smaller weight to the left. Again, somewhat natural, but you could do it otherwise. And for the last case, when we have 2 trees that have the same weight, then again, you put that one left that contains the character that's the smallest in the alphabet. Okay? So these three rules make the algorithm unambiguous. It takes away all the choice and means whenever you have weights, you arrive at the same result. All right. You've seen how to construct the Huffman tree and the code from that. If you want to apply that for compression, you need one thing on top of that. You somehow need to get the frequencies of the text, the character frequencies. So the overall encoding has two phases. The first pass over the text counts how often each character occurs. Then we can construct the tree with the algorithm you've seen using our priority queues and all that. But then we also have to somehow store the Huffman tree or the code that we get from it. Because the decoder needs to know what the code was like to decode. And the decoder cannot use the character frequencies because it hasn't decoded the text yet. So we have to store the tree in some way. Now, we'll not discuss how to do that in a smart way. It leads us too far. A simple way would be to just write down all the code words for the symbols in alphabetic order. It's not impossible, but you also have to say how long they are. There's slightly smarter ways using the tree structure. But we'll never do that in detail. So you don't need to worry about that for now. I just want to mention if you implement this in practice without anything on top, you need to somehow store the tree now. And then only in the second pass, you do what we've seen on the slide. For each character, you produce the code word. With that preparation, you can decode by first reading the description of the Huffman code. Then you know how decoding works. And then you start reading from there using the decoded Huffman code. And you may notice that decoding here is simpler because you do a single pass. You don't need counting first and then encoding. That's a quite typical thing. For many more interesting compression algorithms, the decoding is much easier. And intuitively speaking, I think that's quite obvious. The encoding has the tough job of you're given some text and you have to find patterns, redundancies to compress. That's the hard task. The decoding is just reading the description and producing what's written there. That's pretty much following a script, whereas encoding is writing the script from the source text. So we often need more effort, more time for the encoding part. Let's spend a little thought. Again, I'll go over this fairly quickly, but let's talk a little bit about why Huffman's algorithm is giving you the best possible code. I've so far just claimed that it does, but pointed out that it has this absurdly myopic point of view. Right? What it did is it said the low weight characters should probably get a long code word. So let me just take the two with the lowest weight and lump them together and decide that they get the same prefix. Why on earth should that be really the best possible way? Maybe there's a much smarter way. It turns out no. Let's see why. So this is the formal statement says if we have an alphabet and the weight, that was the input for Huffman's algorithm, then the output of Huffman's algorithm, namely these code words, give us the minimal expected code word length. So that's the sum over all the characters that we've seen before. Weight of the character times the length of the code word. And we can prove this by an induction over the size of the alphabet, which essentially follows the structure of the algorithm as well. And I'll only really show the inductive step. So the basis is you have two characters. If you have just two characters, there's really nothing else you can do than assigning one the length, the code word 0, and the other the code word 1. And that's the only code, so this is the best code. It's kind of not very interesting. But it's true that Huffman produces this code if you start it with two letters. For the inductive step, we assume we have some alphabet size greater to. And then we'll start with an optimal prefix-free code that we don't know what it looks like, but we know there is one. We can't maybe construct it, but from a proof perspective, we could just assume that it's given to us, and we'll argue about it. Because this is a code trie, just from the structure of the tree, there will always be two siblings at the largest depth. Now, what this means, there's some path. So there's the height of the tree, and there's some nodes that look like this, two leaves at the lowest level. The reason is just it's a complete binary tree. We can't have a single leaf at the lowest level. That just wouldn't be complete. You always need some other sibling, and that can either go even deeper or it can stop. But if that's the lowest level, it has to stop. And so we have to have some node like this. And then there's some x and y at this depth d. Now, that may or may not be the two characters that Huffman's algorithm combines in the first step. And in particular, it could not be. But if we have okay, I have different notation for the nodes and for the characters in the nodes. So maybe I should make these a little bigger and write A and B inside. So what's inside the leaves is the character that's represented there. And the node itself is called x and y. If we have some leaf that's further up, and suppose A or B would have been up here, then there would be some other character down there, maybe C, that has larger weight than A. If I keep the rest of the tree the same and swap A and C, what would happen? In this sum, I would move C further up, so it gets a smaller weight, and I move A down. So I change the sum only by these two terms. But the weight of C is larger than the weight of A, so I only get a better code if I do that. So moving to this situation where we have A and B in the lowest. That didn't copy. Only makes the tree better. We had that before, right? Okay, I'm not going to copy it. That's what this says. If I make this change, I would only make the tree better, but because it was already optimal, it has to have the same cost. That means I can always put the two smallest weight characters in these adjacent, in these sibling leaves at the lowest level without making my code worse. And so I might as well combine these two as Huffman's algorithm does. So formally, if I take any optimal code for the alphabet where I remove A and B and put in this combined character, I get something like this tree on top with a leaf here with A and B. If I take that code and unfold it again by replacing AB with this little cherry tree, an internal node and two leaves, then I get back a code that has the same cost as my E star. And so it has to be also an optimal tree. And that concludes the inductive step. what we still need to show is that Huffman's code finds such a tree, but that's by the inductive hypothesis. If we go to one smaller, I said here, let's take an optimal code for this smaller alphabet, but we applied Huffman's code now on a smaller alphabet. So by the inductive hypothesis, which we prove bottom up, we already have the statement for that smaller alphabet. So we can apply Huffman's code to find this optimal tree for sigma prime. Doesn't have a name.